Thank you for that introduction. A couple weeks ago, one of my colleagues sent me this news story, which is about two teams of physicists who are studying what happens to water when you freeze it. And it's actually quite interesting because everyone knows that water freezes at 0 degrees Celsius, except that's not quite true. Water will freeze at 0 degrees if it has impurities in it, like dust and dirt, because ice crystals will form around them. But if you take out all the impurities, you could get water down to negative 20 degrees, maybe negative 40 degrees Celsius before it turns into ice. And when you do that, something really interesting happens, maybe. We don't actually know because it's quite hard to observe, but you can study it with computer models. And that's what these two teams of scientists were doing. One team was from Berkeley, one team was from Princeton. They're using the same computer models and basically the same methods, Monte Carlo simulation, to find out what would happen to water as you supercooled it. And one team discovered something really interesting, that water sometimes would turn into a second state of liquid before it would turn into ice. But the other team found nothing at all. Water just gets colder and turns into ice. And at first, the two teams worked together to try to figure out who was wrong and who was right. But they quickly began fighting, and it turned into this 7-year-long feud, a feud that only ended last month when one of the teams, through asking, threatening, and appealing to a higher authority, in this case the journal Nature, got access to the other team's code. And what did they find in that code? Well, they found a bug, of course. And so it turns out water might do something really interesting because the simulations that said that it doesn't were using bad code. I like that story because it shows that code matters. And if you're doing science, your code might matter more than your conclusions. And that's the message of a book that I helped write this summer called R Markdown, The Definitive Guide. R Markdown is a free R package that creates an authoring format for data science. If you want to understand what R Markdown is, picture a Microsoft Word document and an R script, and then imagine them having a baby. And then imagine that baby getting bit by a radioactive spider and developing superpowers. R Markdown's pretty amazing, and we'll have a chance to talk a little more about that later. But there's two reasons that I'm very proud about this book. The first is it's available in its entirety for free online at this web address. And the second is we've made it as cheap as we can to purchase a physical copy. Shortly after we finished writing it, Yue, the chief author, emailed JJ and myself and said, look, I've talked to the publisher and I've sort of struck a bargain with them. They will reduce the cost of a printed copy by the amount that they normally pay us for a royalty. There's only one catch. And the catch was we wouldn't get that royalty. And I can assure you that writing books is actually hard work. And believe it or not, they make money even when you put them online for free. So giving up the royalty might seem like a silly thing to do, but we all agreed to do it. And we did that because R Markdown is going to solve the reproducibility crisis. You may not realize it yet, but the reproducibility crisis is the one dark cloud in the otherwise bright future of data science. And it's a darker cloud than you might think. Basically, the reproducibility crisis, something that came around the year 2012. At that point, well, let's not get ahead of ourselves. First, I do assume that most people here know a little bit about the reproducibility crisis because it's been reported on pretty widely in scientific journals like Nature. Also, it's been reported on in the public press. You might have seen it in the Wall Street Journal or the New York Times. And what it amounts to is this. Pharmaceutical companies recreate academic studies as part of their work. They do this to determine whether or not those studies could be developed into viable products. Normally, when they do this, they keep the results to themselves in-house. It's a competitive advantage. They're for-profit companies. But in 2012, the Amgen pharmaceutical company noticed a picture that disturbed them so much, they decided to go public with it. And what happened was Amgen had recreated 53 landmark studies. Landmark is Amgen's word, but what that means is they're all published in prominent journals, and they had influenced future research. And what Amgen noticed was they could only replicate the results of 6 of those studies. From a scientific viewpoint, that's really bad. That means these other studies might as well be wrong. In fact, they probably are wrong. And yet they were all published in prestigious journals, and they had gone unchallenged in academia. After Amgen sounded the alarm, the Bayer company, another pharmaceutical company, confirmed that when they recreate studies, they can only replicate the results of published work about 25% of the time. Since then, we've studied this issue in a lot of detail, and our best estimates are that 75% to 90% of preclinical results cannot be reproduced. Again, this is bad. That means those results are maybe wrong, they're ephemeral, and they're coincidence at best. This costs a lot of money because it costs a lot of money to run these studies, and then the studies feature other work which also costs money. And we have an estimate of how much it costs to have this irreproducible research. And that estimate is that it costs the United States biomedical research industry $28 billion each year. Now, to put that into perspective, with $28 billion, you could buy a latte for everyone on the planet from Starbucks. Now, if you're like me and you don't really have a good sense of how many people are on the planet, we could formulate this in a different way. With $28 billion, you could buy everyone in this room, and there are quite a few of you, your own private island in the Bahamas, assuming supplies last. And that's just the money that's wasted in 1 year in the United States in the biomedical field. And unfortunately, all indications suggest that this irreproducibility problem extends well beyond biomedicine into all research. For example, a survey of prestigious economic journals showed that out of 18 studies, you could only replicate the results of 6 of those studies. And then another survey of articles published in Nature and Science showed that you could only represent 13 results of the 21 studies surveyed. Now that's disturbing because Nature and Science publish articles from across the fields of science. Not only that, they're widely considered the 2 most prestigious journals in scientific literature. And so while 13 out of 21 isn't quite half bad, that'd be 10.5 out of 21, it's still very alarming. And you should be alarmed. The results of this research, the results of irreproducible studies, darn that word, are useless, but they've become a part of the scientific consensus, and we don't know which part. We've seen that there are billions of dollars at stake, but there are other costs as well. These studies are designed to do things like create wealth, heal the environment, and cure cancer. But they can't do that because they're useless. And worse than that, they're distracting the people who would otherwise be solving those problems. Now, I don't know about you, but I would like it if scientists cured cancer before, I get it. And I like the idea of a healthy environment, too. Also, there are academic reputations at stake here. That I'm not so concerned about. I'm not writing about our markdown talking to you guys because I care about the academic reputations because, to be frank, I question whether there's an incentive in academia to fix the reproducibility problem. Like it or not, lax standards for publication makes it easier for professors to publish articles, which is imperative for their career advancement. The reason I'm talking about irreproducible research for you guys is because if your company is intimately associated with data science, then the reproducibility crisis is for you a credibility crisis. The studies I've mentioned come from many different branches of science, but they all have one thing in common. They all use data and they analyze in sophisticated ways. Like it or not, academia, and presumably the readers of the Wall Street Journal and New York Times are starting to realize that data is not a panacea, and neither are sophisticated ways of analyzing the data. And it gets worse. The reproducibility crisis is just one aspect of what could amount to a looming credibility crisis for data science. Let me share some more familiar stories. So think back with me to a recent example of a data crisis, data science failure. Where were you on November 7th, 2016? I know we're not in the United States, but you might have been following the United States presidential election. If you were the typical American, you probably started the day by going online to your favorite news site and seeing what the predictions were for the election that would happen that night. And this is, well, I'll show you some of those predictions in a second. But before we go do that, think about what this average American would have thought. There had been a lot of stories in the election cycle about how advanced polling had become. The American presidential election is like a sporting event. No, it's like a whole season of sporting events. And there have been plenty of stories about modern methods of data science that use things like Bayesian models and other types of models to create really accurate results. You probably knew as this average American that there's some guy named Nate Silver who had predicted the last presidential election like 110% accurately. And so when you saw these polls, you expected them to be right. And this is what you would have seen. This is the poll from the morning of the election from the Huffington Post, which is a popular news site. They gave Trump a 1.7% chance of winning. To be fair, the New York Times gave Trump a 10% chance of winning, and Nate Silver gave Trump about a 30% chance of winning. But this is a real poll from a real popular website. And look, they used a model that says right up there in the top line. So you knew that this was trustworthy. And depending on your political persuasion, you probably spent the rest of the day either really dejected or really happy. But then the election happened, and I forget. Was this poll accurate? Do you think anyone noticed? Here's another story. In 2015, a big tech company developed a machine learning algorithm that could classify photographs. They quietly inserted this algorithm into their photo app, and so the next day, without warning, millions of users went online and discovered that their photographs had been classified for them. Now, if you ask me, that's pretty creepy, but it got worse. This happened. Do you think anybody noticed? I forget the name of that company, but I'm sure you could Google it. The next year, Microsoft developed an artificial intelligence that could communicate with people on Twitter in a realistic fashion. In fact, I think it could pass the Turing test. Microsoft must have been very optimistic or perhaps unaware of the Terminator movies because at 7:14 a.m. on March 23rd, 2016, Microsoft connected this AI to the internet and invited Twitter users to communicate with it. And then something went horribly wrong. 10 hours later, the AI was saying things like this. And Microsoft had to go back and clean up its timeline. Now, to be fair, the people talking to it were saying similar things, so. Let me tell you a more personal story about data science and credulity. Now, keep in mind, I am a data scientist, so I'm not too incredulous, but when I was in grad school, I decided that I was going to use the university gym to get incredibly buff. And as part of that process, I stopped eating bread and started eating a lot of meat and fat because some dude told me that's how you get buff. Well, you can see how that worked out. But something interesting did happen. I started feeling a lot better, and I started losing weight, the type of weight that you want to lose. And this is peculiar because the United States Department of Agriculture, which does our nutrition research, has official guidelines on what a healthy diet should look like. This is the actual food pyramid that they promoted throughout the 1990s that encapsulates these guidelines. They've modified a little bit since then, but you could see that they think a healthy diet should include a large portion of bread and grains, and then a lot of the other types of carbs. And you should only eat a little bit of meat and almost no fat. I was taught this as a young person. I don't know who eats 6 to 11 servings of anything a day, but so look. This food pyramid is based on 50 years of hard science, observational studies, and meta-analyses in nutrition. But the USDA hasn't always had this as their guidelines. They released these guidelines about the mid-'80s. And when they did, American industries, food industries, responded very quickly by removing fats from their products and replacing them with healthy and conveniently shelf-stable grains and sugars. The American public responded by slowly and horribly becoming obese. This is the official visualization of the American obesity epidemic by our Center for Disease Control. And the epidemic began about when these food guidelines changed, and it continues to this day. So this is really peculiar. People, presumably following these dietary guidelines, are getting obese, but I, throwing science and caution to the wind and eating incorrectly, was getting, as far as I could tell, healthier. And I'm not the only person who's had this experience. If you go to Amazon.com and look at the bestseller list for diet, nutrition, recipes, anything like that, you'll find books like this up there. These are the most popular eating guides, and they're all based on eating lots of fats and less carbs. So think about diets you've heard of that people claim work. The Atkins diet, the South Beach diet, paleo, keto, primal, whatever. They're all some iteration of eat fats and don't eat carbs. So these things have sustained popularity. I know diets are, a weird industry anyways, but I think there's some credibility to them. And I think that the people who are reading these books believe that the science that diet wisdom is based on is wrong. In fact, I know that they believe this because Amazon tells me that people who read these books also read these books, which are science books that critique the past century of nutritional information, in my opinion, with good cause. So what does all this amount to? Well, I got into statistics and now data science partly because I like to see myself as a type of Sherlock Holmes, the original consulting detective. And as data science became more popular, I was happy that other people began to see me in the same way. Now, some of you in this room are actual consulting detectives, real-life Sherlock Holmes. But your customers are starting to have a growing and legitimate concern that data science does not deliver very effective results. Now, of course, I don't believe that, but I do believe that we should address the concern. And we can do that if we know what's causing this problem. And I could tell you what academia is thinking causes the reproducibility crisis, so we could start there. I don't ultimately buy academia's story, but it's something to think about. And I could tell you this because last month, the American Statistical Association published an article about it. The article appeared right alongside the cover story about R, which is also a good read. Their explanation relies on a metaphor that involves cargo cults. Do you guys know what cargo cults are? Cargo cults are a phenomenon that occurred in South Pacific Islands following World War II. These are very isolated islands where the native populations basically had a Stone Age culture, but during World War II, servicemen from Britain, the United States, Japan would arrive, they'd plow out airfields, they build communication towers, and then miraculously, from the natives' point of view, planes would descend from the sky laden with cargo for the war effort. Some of this cargo inevitably would make its way into the native hands where they'd find it very useful. But then the war ended and planes stopped coming and there's no more cargo. So what were the natives to do? In some places, they recreated the technology they had seen. They built reproduction planes, reproduction landing strips, reproduction radio towers, and then they waited for the planes to return. They tried to use this technology that they didn't understand to get the results that they'd seen other people getting with the technology. And that's the metaphor that the ASA uses to describe the replication crisis. The ASA says that many applications of statistics are cargo cult statistics. Practitioners go through the motions with scant understanding. In other words, people who are analyzing data don't know what they're doing. That's the story. And there's something to this story. I mean, there's reason to pay attention to it. If we think about this metaphor, one of the original airmen who had real airplanes landing would probably be like Ronald Fisher, one of the original statisticians. And we could look at how he did statistics. This is an example, a worked example from his book, Statistical Methods for Research Workers. And it starts here with the blue text, and this is how he goes about solving his problem. He states his problem very precisely, he discusses it, he identifies important characteristics of the problem, he identifies assumptions that he could work with, and then he invents from nothing a method that can help him answer his question about this problem. He runs the method, and then he interprets the results. And so 4 pages later, we have his answer for this question, which is something very simple, is like, are twins of criminals more likely to be criminals, based on the data? Now let's compare what Ronald Fisher did to what a modern data analyst might do, at least one who doesn't know R. They might collect their data, they have it, they open up some software, and then they say something like, I have these 20 tests to choose from, so I'll pick this one. So I could see why the ASA thinks that people might just be misusing statistics. But ultimately, I don't buy that story, and here's why. First, it's a little too convenient. I mean, the story basically is, hey, look, statisticians aren't the problem. No, we're part of the solution. You just need more of us. But I am a statistician. I have a PhD in statistics. And I saw where my office mates went to work after they graduated with their PhDs in statistics. And where do you think that was? Biomedical research, someone in the financial research. But they went to work into the industries where the reproducibility crisis exists. That's where statisticians work. So I don't quite buy the answer that it's a lack of statisticians that are causing the problem. The second thing is, you could use statistical methods exactly right in a very expert fashion, and you will still have a reproducibility crisis. Let's look into that. When people talk about the reproducibility crisis, the word p-values almost always comes up. We're doing p-hacking. We're using p-values incorrectly. If people just understood p-values, we'd be okay. Well, despite what we tell ourselves, p-values and statistical methods aren't actually rocket science. I'm certain that anyone who could get a PhD in anything can understand a p-value. Yes, it does involve a double negative, but you can think about double negatives, especially if it's your job, like it is for these people making these studies. What a p-value does is something very specific. Normally, it means, well, the presence of a p-value always means that you've done some sort of statistical test, and most statistical tests address this bit of uncertainty. If you're collecting a sample from a population, there's uncertainty that is introduced based on sampling variation, and a p-value helps you quantify and deal with that uncertainty so you could reason about the results. The thing is, this uncertainty is only one source of uncertainty that exists in a typical scientific study. So this is a graphic that my friend and colleague Drew Levy helped publish, and each of these gray labels here is another source of uncertainty that exists in a typical scientific study. So why is it that we assume that when we account for this bit of uncertainty, it justifies the whole process? And let's be clear, that is what we're doing. Until very recently, if you submitted a study to a major journal, they would check to see if you had a significant p-value. Here's two things they would not check to see if you had included: your data and your code. So why are we doing this? Why do we think that this one step justifies our conclusions? It's not a rhetorical question. I have an answer. Don't worry, I'm going to impose it on you. But I want to try to convince you, and I'll start with Ronald Fisher's example that we had here. This is just one of those 4 pages we looked at. What does this look like to you? I mean, take a minute and just look at it. You'll probably notice algebraic variables, some formulas. I think it looks a lot like math. I mean, some of it undeniably is math. Why might this be important, though? Well, let's do a thought experiment. Here's 2 groups of words. Look at them and decide which group of words is more associated with math. All right. I'm going to guess that you're not choosing hypothesis, messy, best guess, and discover. Not unless you're very new to math or very advanced in math. The beauty of math is it's so precise, it's so logical. When you do math, you can prove things, which is why we love to use math. But now think about science, like getting your hands dirty, scientific methods, science. Science is associated with the other group of words. When you work in science, you only ever have hypotheses that represent your best guesses. You might discover new facts that help you select from among your hypotheses, but you never are able to prove anything. Now, these 2 systems of learning are very complementary. Math is great, but as a system of logic, it can only reveal information that is already present in your definitions and your premises. But math cannot tell you whether those definitions, which in the case of math involve the definitions of numbers and numerical models, accurately correspond with reality. Science can do that. The point of science is to help you identify definitions, as it were, that correspond to reality. These definitions are always estimates, but they're the most useful estimates that you can use. As a scientist, you should understand that they're subject to being invalidated or redefined later on, but that's how science works. Science never proves its definitions. Science never proves anything. Now, some of you who are fans of hypothesis testing might say, well, wait a second. You can prove things in science. You can prove that a hypothesis is wrong, and that's something. But actually, you can't. If your work involves a probability model, there will always be some probability, even if it's very small, that your hypothesis is true no matter what your p-value is. We just, by custom, round that probability down to 0 if it's less than 1 in 20. And that's the point. We use statistical tests and we use p-values as if they were mathematical proofs. They look like they're math, so we feel comfortable doing that, but they are not math. They do not prove. A statistical test does not prove something. We use statistics to precisely define things that are absurd to try to define precisely, like the amount of uncertainty that's involved in something. And we feel comfortable doing this because our methods resemble math, they use math, they look like math. So I think the ASA was right when they said that there is a cargo cult phenomenon happening here, but I think the cargo cult is that we have confused science with math, and we think that we are mathematicians going out proving things, and then we don't understand why the derivative works end up being irreproducible. This is my one piece of evidence I'll share with you. These are 3.4 million p-values that you can get from articles published on PubMed. And you could see the scale only goes up to 0.5, but by far the most p-values that you see published occur around 0.05, which is the culturally accepted alpha level for statistical significance. I think the reason this is happening is because researchers who create studies, who, by the way, have some control over what level p-values the studies can return, and reviewers who evaluate studies treat 0.05 as if it is a proof that the results are correct and publishable worthy. In short, we can now answer our question, why do we think this one step, this one p-value over here justifies the whole process? Because we've created a cargo cult by confusing math with science, and now we must undo it because we're the data scientists. And it's not that hard to do. Actually, everyone in this room, every scientist knows how to do this correctly. We've just sort of forgotten. We have a wonderful example to follow if we think back to the age of exploration, right? That's when we were discovering different continents and whatnot. The explorers were going out into the world trying to find and document previously unobserved parts of reality. And that's exactly what scientists do. And so we could use them as an example of how to do this well. Think of Christopher Columbus. When he sailed across the ocean and he discovered the United States, well, I'm a little culturally biased there. When he discovered America, he didn't sail back to Spain and then deliver a logical proof that convinced everyone that there was a land across the ocean. Instead, he gave people a map, and if they followed his map and got to the New World, then that spoke for itself. If they followed his map and they didn't get to the New World, that also would speak for itself. But there's no way he could logically prove the existence of the New World. As scientists, we're in the same boat. What we should be doing is creating maps for other scientists to follow and not trying to prove scientific knowledge, because we can't. Scientists traditionally have been very good at this. We have a very good culture of creating maps that other scientists can reproduce that take us from our questions about nature to the actual data we have. The typical scientific report does just this. That's the thing where you talk about your materials and your methods and you discuss the results. And back in the days when data was synonymous with your conclusions, that satisfied. But things have gotten much more sophisticated now. Now there's a whole back half to this journey, going from the data to interpreting it and creating conclusions. And we haven't learned how to create reproducible maps that could take someone from our data to our conclusions. And to be fair, it's a tough task, because if you want to help someone do this journey just as you did it, you have to provide a lot of things. First, you have to provide your data, but then nowadays you have to provide the code that you use to analyze that data, which means you also have to provide the software that runs that code. And then on top of all that, you need to provide the reasoning that guided your decisions every step of the way and then interpreted the results when you're finished. So that sounds like an impossible combination of things, or a lot to juggle, but we have a very good way of doing that, because this is what R Markdown does. So now we're back to R Markdown. R Markdown is an authoring format for data science that allows you to give people your data, your code, your software, and your reasoning to create a reproducible map that they can follow to get to your conclusions. And amazingly, R Markdown gives people more than the map. Your R Markdown file is itself a vehicle that they could use to travel the distance of the map in a very easy, effortless process. Now, I could tell you more about R Markdown, but I'd rather finish by just sharing a story of someone who uses R Markdown to do a good scientific job. So the hero of this story is, not my computer's resolution. All right. Well, the hero of the story is a data scientist named Bill. This is a picture of his forehead. Bill proudly works for a brewing company where his colleague, Vice President Virginia, calls him up and tells him, look, Bill, ever since we replaced our bottling machine, customers have been complaining that we're not putting enough beer in the bottles that we sell them. So can you please go down to the factory and check that each bottle is leaving the line with, on average, 750 milliliters of beer. So Bill, who's going to remain incognito, dutifully goes down to the assembly line. He takes a random sample of 50 bottles of beer as they come off the production line. He measures the amount of fluid in them, and he puts it into a company spreadsheet. Then, since Bill loves reproducible research in R Markdown, he opens an R Markdown file, which looks just like this. It's a simple plain text document with formatting that's done with plain text inside the document. This one's empty at the moment. It's very easy to share. It's very easy to put on like GitHub. It's very easy to look at and interpret the diff of such a thing, because it's all just text that you could read. And inside an R Markdown document, you could put R code by putting in code chunks. So we put some code chunks in here. This code's very simple. It's going to read in its data from that spreadsheet. It's going to calculate the mean of those 50 bottles. It'll save that as observation, as a sample observation. It's going to do a simulation. It's going to make a plot. It's a short document. Bill can use this document like a notebook, like a Jupyter notebook, if that's how he prefers to do things. He could run each code chunk, and the results will appear in line in this document. So here's the plot he makes. To this document, Bill can add text that explains his reasoning. So he could go in there in between the code chunks and write some narration. So this might sound really pedantic, but let's read what he writes. It's only going to be 4 paragraphs, and it's going to explain a t-test, something that Bill feels very confident making. So first he says, here's what I'm doing. Does our bottle machine fill each bottle with 750 milliliters of beer on average? Next, here's my data. I selected 50 bottles at random from the Dublin factory, which contain the following amounts of beer in milliliters. The amounts are going to appear because the code's going to insert them. The next piece of text is going to say the mean amount is, and this is our Markdown syntax that says, add into the text the value of obs, which is an R variable. When the reader reads the final document, it'll just be a number that happens to be the value of obs, which is the sample mean in this case. Next, he's going to explain his reasoning. He could just do a t-test and give the p-value to somebody, but to create a reproducible map, you actually need to inform the person what you're doing so they could judge you each step of the way and look for discrepancies. So his reasoning is this. The amounts of beer in our bottles should be normally distributed with a mean of 750 milliliters and a standard deviation of 3 milliliters. Why? Because that's what we believe, or that's what the bottle machine manufacturer told us would happen. Next, let's use simulation to calculate the sample means of 1,000 samples of size 50 generated from such a distribution. And that's what's in that plot that the code will provide. And then he sums it up for Virginia. I've plotted the distribution of the simulated means above. The blue line shows our observed sample mean. Notice that some value calculated in R % of the simulations produce a sample mean as extreme as ours. That means our p-value is this, by the way. In other words, our observations are in accordance with our belief. And to really hit the nail on the head, the conclusion is we do not have evidence that the bottle machine is malfunctioning. Now, this is an R Markdown document. It looks kind of dirty the way it is, but part of the point of R Markdown is you could then take this document, you could run all the code in it, and use it to generate a nice report that you pass off to the person you want to impress. So Bill can go up here. At the top, there's a line where you can say what sort of report you want to make. So it's R Markdown. He can make a PDF report. That report will look like this. He's choosing not to put the code in it, just the results. And so it's a very human-readable thing that you could give to a boss or a customer. You don't have to settle for PDFs. We can make a PowerPoint presentation. I'm not a PowerPoint guy, so please forgive my lack of templates. This is actually shown up in Keynote because I use Mac. But you can make PowerPoints. You can make dashboards. You can make books. You can make blogs. Basically, you can make almost any format that you want to make from the same R Markdown file. In this case, Bill's just going to make a simple HTML document, which looks like this. HTML is good because HTML is made to go online. And Bill's company uses RStudio Connect, which is a service for putting our artifacts online. So he could click publish and, configuring just a few things, he could put this online at his company's internal server. And then if he wants Virginia to take a look at it, he could add her as a collaborator. And he could email the report to all of his collaborators. So now Virginia has this report. And she could read through it, and she could say something like, oh, that's what a p-value does? That's not that impressive. Maybe we should come up with better tests. All right. But there's one more thing I want to share with you guys. Making a reproducible map like that is actually an opportunity, because if you could reproduce the work, then you could repeat it. And if you put everything that you need into that document to reproduce the process, then perhaps maybe even a computer could repeat it for you. And once you get to that point, well, then the sky's the limit. Say Virginia comes back and says, hey, can you do this for me every week? We found it really useful. Well, then Bill can say, yes, actually, I could ask the computer to do it for you every week because I put in there everything we need. I'll go to RStudio Connect, I'll schedule this weekly, I'll make sure it sends you an email each time it runs, which will be on Mondays. And I'll hire some intern to make sure we have 50 new bottles every Monday. And then he schedules that to happen. Done. Bill can go enjoy himself. Or maybe Virginia says, hey, look, Bill, this is a company secret you don't know about, but we have a second factory in London, and it's having the same trouble. So can you go there and repeat this analysis for the London factory? Well, once again, Bill says, I've already done most of the work. I just need to repeat it with some new inputs. So I'm going to add some parameters to my document up here using the R Markdown syntax. I'll change the code just a little bit so it uses those parameters. And in this case, I'm going to change it so some of the text is generated by R code, just in case London, the machine is malfunctioning. I want the document to say that. If it's not, I want to say what it previously said. Now when he relaunches this, it's going to appear, because it has those parameters in such a way that Virginia has a little input tab over here, that Virginia can click at her leisure. It will open up the parameters that Bill put into the document, and then she can, again at her leisure and initiative, choose which parameter to use. Does she want to look at the Dublin factory or the London factory? She could run the report, and then she gets a result. And if you looked at the report closely, you'd see it's talking about the London factory. And not only that, at London, the machine is malfunctioning, and the conclusion text explains how we know that. So she likes it. And all this works because the R Markdown document contains everything that you need to reproduce your analysis, whether that reproduction is be done by another scientist who wants to verify what you're doing, or whether it's be done by a computer that's leveraging what you're doing to create more value and more efficiency in your company. So what I want you guys to do is to go familiarize yourself with R Markdown. It's completely free, and use it. Use R Markdown because it's good for science. Use R Markdown because it's good for data science. And use R Markdown because it's good for business. It creates opportunities. So let's finish with one final opportunity between Bill and Virginia. What should we do with all this beer? All right. Thank you very much.